Hello, welcome to episode -4 of the LearningMeasure.tv podcast. I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. As you saw last week, there were still problems with the whiteboard. We'll try to avoid using the whiteboard except for when using equations for the moment until we figure out a better way of doing the lighting. Little progress report of what's been going on. We got the RSS feed working. We've submitted this podcast, iTunes and Podcast Alley. We'll probably do a few more later this week. Basically, what we're going to do this week is continue on with my our measurement-related topic from last week. This will be the last week we do that, and next week we'll start with some more general things, and the idea I want to start next week is with antennas. We'll define some terms and measurements for antennas. So right into the feature part of this, we were going to do an interview this week, but the person who was going to interview didn't show up. We'll see how that goes next week. Anyway, first of all, I want to talk about measurement and metrology. Metrology is the science of measurement. It has nothing to do with the weather. You may have heard the term meteorology. Not related. Metrology is the science of measurement. And in the metrology world, there are international standards in the measurement world that are used to define terms and how you do certain things in measurement. A lot of these standards come from the International Standards Organization. In particular, there's two: ISO Guide 99, which is called the International Vocabulary of Basic and General Terms in Metrology, also known as the VIM, and ISO Guide 98, the Guide to Expression of Uncertainty in Measurement, also known as the GUM. Another related standard for calibration and testing laboratories is the ISO IEC 17025 standard, which is the general requirements for the competence of testing and calibration laboratories. So what we're going to talk about now are some terms that are those standards defined. Last week we talked about uncertainty. Well, this week we're going to, the actual GUM definition of uncertainty is a parameter associated with the results of a measurement that characterizes the dispersion of the values that could be reasonably attributed to the measurand. So, again, like I said, it's a number that characterizes how far the measured value could conceivably be reasonably attributed to be from the true value of the measurement. And the ISO breaks uncertainties into two categories. Type A, you have type A evaluations of uncertainty, which is a method of evaluation of uncertainty by the statistical analysis of a series of observations. Something like standard deviation might be or variance would be measures. In some cases it might be something like Allen variance or something else, some statistical measure of a series of observations. Type B evaluations of uncertainty. Method of evaluation of uncertainty by means other than by statistical analysis of a series of observations. In other words, anything that's not a type A error is a type B error. These terms have nothing to do with the older terminology of things like systematic errors and random errors. You could have type A components that were systematic and random, or type B components that are systematic and random. The other thing important in measurement is a concept called traceability. The VIM defines traceability as the property of the result of a measurement or the value of a standard, whereby it can be related to stated references, usually national or international standards, through an unbroken chain of intercomparisons, all having stated uncertainties. So the important things here is that traceability, the value of a standard or the result of a measurement is traceable. Sometimes people say that standards are, like measurement standards are traceable, or piece of test equipment is traceable. That's improper terminology. Only the result of a measurement or a value of a standard can be traceable. Another thing is each intercomparison, there's an unbroken chain of comparisons, all having stated uncertainties. Each step along the way, an uncertainty analysis has to be made back to the national or international standards. For a traceable measurement, the result has to have several things. The parameter that is being measured has to be clearly defined, for one. You have to have a complete description of the measurement system or standard used to make the measurement. If you don't have that, you can't really say the measurement's traceable, because you don't really know how the intercomparison was made and whether it was adequate or not. Of course, you have to have the measurement result and documented uncertainty for the result. And another thing that is often considered critical is that an internal measurement assurance program must exist, and that's for the purposes of establishing the status of the measurement system and the stated reference. One more term from the VIM that you may understand is calibration. Calibration is defined as a set of operations that establish under specified conditions the relationship between values of quantities indicated by a measuring instrument or measuring system, or values reported by a material measure or reference standard, and the corresponding values realized by those standards. So calibration is establishing a relationship between what something measures and reference standards. Calibration is different from adjustment. Those are the definitions I wanted to go over. And now what I wanted to go over next, we talked a little bit about measurement equations. I want to be a little bit more specific. You can have a measurement equation now. Let's say y is the quantity you want to measure, and it might be a function of several variables. Let's say n variables. These could be, in our example last time, it was there was two variables, length and width, to measure area. Well, this can be this is just a more general measurement equation. Now, often we know somehow, some way, we won't know how you get into those yet this week, but you may have uncertainty estimates for each of these quantities that make up the measurements. Let's call them delta x1, delta x2, delta xn. Somehow you know the uncertainties associated with each component of the measurement. Okay, the question you want to know is, what's the uncertainty of the measurement? Let's call it delta y. Well, one way you can do that is by doing essentially a first-order Taylor series expansion of the measurement equation, and which gives you how it changes, to approximate the equations for small changes around the value. Well, you can do this by doing this. So what we have squared. This is a first order Taylor series expansion. Each term is the derivative of the measurement equation with respect to each variable times its uncertainty squared, and that's RSS for this first term. This second term, this last part here is the covariance between two variables, xi and xj, and the two partial derivatives. We're not going to deal with that here just because of time, but maybe in a later time we can go into how you deal with that. So a good estimate then for the uncertainty that's the RSS uncertainty, is just the sum of all the derivative with respect to each variable times its uncertainty squared, summed up, the RSS. I'll give some examples next to make it easier to understand how this works. Last week, we had a simple measurement equation that we did for an area. Area equals length times width. Okay? The uncertainty in the area then is going to be square root of, the derivative of this with respect to L is W, so it's W delta L squared plus L delta W squared. Oftentimes you want to know the relative area. Relative error in the area, uncertainty in the area. So that would be delta A over A, which is equal to this, square root of W delta L squared plus L delta W squared over LW. Well, putting that in there, you end up with L squared over L. You can work this out for yourself. It's not that hard. Or better yet, write it like this. So this is just saying the relative uncertainty of the area is the RSS of the relative uncertainty of the length times and the relative uncertainty of the width. Very simple one. Let's go for a little bit more complicated one. Just as another set of examples. Let's talk about DC power dissipated by a resistor. We have a current source and a resistor. The power dissipated by a resistor follows the equation P equals I squared R. What's delta P? The uncertainty in the power is 2I R delta I plus I squared delta R squared. Okay, this was just taking the derivative times the uncertainty, squaring it, derivative with respect to R times the uncertainty, squaring it, RSSing it. Now delta P over P, relative uncertainty. with just a little algebra, that becomes now in this case, the relative uncertainty of the power measurement, you get the RSS of the relative component of the resistance plus twice the relative component of the current. In this particular case, because of the nature of this measurement equation, a relative uncertainty in the power has twice the contribution from the relative error of the current than the resistance. Now these coefficients up the front, for that reason, are called sensitivity coefficients. It's a measure of how sensitive the uncertainty, relative uncertainty, is with respect to each individual relative uncertainty component, or uncertainty component for that matter. Now, there are examples where this type of analysis would break down. I'll give you one. And let's say this is not you want to measure the power of delivered resistor. Let's say you want to measure the power, the real power delivered to a load. P. In this case, AC power, the power delivered, real power delivered, is the current times the voltage times the cosine of the angle between them. Let's look at the particularly interesting case of theta equal, you measured theta is equal to 90 degrees or pi over 2 radians. Okay. In that case, power is 0. Well, the uncertainty, if you do this first order uncertainty analysis, you get the power derivative with respect to I, delta I, cosine theta. There's 3 terms here, plus derivative with respect to V. And then finally the theta term. Oops, might be sine theta delta theta squared. Well, what does this tell you? Well, if that was actually the measured value, this term 0, this term 0, this term's really small. It may be for this case, a first order uncertainty analysis is inadequate. Now, the other thing that's really weird about this is if you look at the relative uncertainty, something really strange happens. And it's related to the fact that you're measuring 0. You end up with, now this is kind of weird because these term was 0 here, this term was 0 here. Now in the relative uncertainty you've got this. so you end up with this one term, tan theta, delta theta. Well, 90 degrees, that's an infinite, so the relative error is infinite. That could be a problem, but that can actually happen. Now, the reality of the situation is the relative error really is going to be very large. The fact that it's infinite is a result of just handling the first order terms. But it's going to be very, very large because you measured 0. But you know, with a little work, you can go to second order, and you'll find out you'll have terms that can make this go better. But that's a lot harder. So we gave several examples of how you can compute uncertainties given a measurement equation and the uncertainties involved in each term. This is kind of very math intensive, but it's actually fairly straightforward once you've done a few of them. Like I said, this is going to be a very short one. This will be the last general measurements one. We're still working on getting some people in to interview. Next week we're going to do something on basic antenna measurements, basic antenna concepts, just because that's an interesting subject to me, and some other people expressed interest in me doing that. So that's what I'll do next week. Again, if you would like to see something discussed in this podcast, something measurement related, a specific measurement, or science related, or simulation related, give us an email, suggestions@learningmeasure.tv. And if you're a vendor that would like to show your wares here or give us a press release or something, send us an email at vendors@learningmeasure.tv. Finally, if you want to be part of our consultant measurements, go to learningmeasure.com and follow the instructions to become part of our consultant network. And if you become a member of our consultant network and you're in the Las Vegas area anytime, we would like to interview you. And you can tell everybody what you're about. That's it for this week. I'll see you next week.